Okay, this is Physical Chemistry, Chapter 15. We're starting Section 5 now. In Section 4, we derived the Maxwell distribution. In this section, we're going to talk about ways to apply the Maxwell distribution. So the first thing we want to do is use it to find average speed in 3 dimensions. So remember, we showed before how if you want to take the average of a continuous variable, a function of a continuous variable, you just take that variable times the probability distribution function. So it's going to be the integral from 0 to infinity, because remember speed's always positive, of the speed times this capital G of V, dV. Remember this capital G of V we derived, that's the Maxwell distribution. So that's going to be equal to the integral from 0 to infinity of the speed times the mass over 2 pi times the Boltzmann constant times the absolute temperature, this to the 3/2 power, remember when 3 dimensions are down, times the natural number E to the minus mass speed squared divided by 2 Boltzmann constant absolute temperature times 4 pi speed squared with dV. That's just speed again. So we're going to pull out the constants now to evaluate this integral. So the m over 2 pi kt to the 3/2, that's constant, it comes out. The 4 pi, that's constant, it comes out. So that just gives us the integral 0 to infinity of the speeds cubed times e to the minus mv squared 2 pi, or 2 kt dv. Now to evaluate that, you're going to have to use a table of integrals. And in the table of integrals, it looks like this. The definite integral from 0 to infinity of x cubed e to the minus ax squared dx. That's going to be equal to 1 factorial over 2a squared, or just simplified to just 1 over 2a squared. Obviously, to get this to match that, we substituted a is equal to the mass over 2 kt. So that tells us that the average speed is equal to 4 pi times m over 2 pi kt to the 3/2 times 1 over 2 m over 2 kt squared. Okay, so that, doing a whole bunch of math simplification, I'm going to leave out those steps because it's just algebra. So that gives us the average speed is the square root of 8 kt divided by pi times the mass of one molecule, or the square root of 8 times the gas constant R times the absolute temperature divided by pi times the molar mass. And remember, that has to be in kilograms per mole, so the units work out correctly. So this is what it tells us. Here's a graph of average speed divided by, or against temperature for a lighter element and a heavier diatomic diatomic element. So you notice, getting close to 400 kelvins, a little above room temperature, the average speed can be somewhere around 1 kilometer per second. But nitrogen is going to have slower molecules because they're heavier. Helium will have faster molecules, or faster average speed, because it's lighter. Now likewise, if we want to find the average of the speed squared, we just substitute it back into the same formula, but we put v squared instead of just v here. And again, I'll skip all that arithmetic, it's a waste of time. That simplifies to just 3 kt over lowercase m, or 3 rt divided by capital M. So you take the square root of that, the square root of your average speed squared, that's your RMS speed. And I think we already showed this before, but now we derived it. So that's either the square root of 3 rt divided by capital M, or the square root of 3 kt divided by lowercase m. Okay, so likewise we want to find the most probable speed, VMP. So remember, we said that if you have the curve, at the peak of the curve, that's where the speed is the most probable. And you know from calculus that at the top or bottom of any curve, the derivative is equal to 0. So that's how we're going to find that. We're going to set the derivative equal to 0 and find VMP. So we're just going to take the derivative of our function, capital G of V, remember v, lowercase v is speed, set that equal to 0. So the derivative of m over 2 pi rt, remember before we had lowercase m and 2 pi kt, but it works out the same. Remember lowercase m and k, or capital M and r, they're interchangeable, to the 3/2 power, times e to the minus m VMP, we've got mp for most probable speed squared, over 2 rt, times 4 pi times the most probable speed squared is equal to 0. Now we're going to have to use the chain rule because of all this, and we're going to have to use the product rule. But first, okay. Okay, so we pull out the constants first. We have 4 pi times m over 2 pi RT to the 3/2 times the derivative with respect to speed of e to the minus m vmp squared over 2RT times vmp squared is equal to 0. Now, these constants, they can't be equal to 0 except in the trivial case where the mass is equal to 0. And we don't have any particles with a mass of 0, so we're going to ignore that case. So, we know if x times y is equal to 0, and x can't be 0, then y must be 0. So if this can't be 0, this must be 0. So now we can say that this derivative is equal to 0. So using the chain rule and the product rule in one step, we get minus 2m vmp over 2RT times e to the minus m vmp squared over 2RT times m vmp squared plus 2 vmp times e to the minus vmp squared over 2RT. All this has to equal to 0. Now, if we take e to anything, it can't be equal to 0. If it goes to infinity or minus infinity, it'll approach 0. So again, we're going to ignore the trivial case where the mass of the molecules is infinity, and we're going to just say, okay, that can't be equal to 0. So if this exponent can't be equal to 0, the rest must be equal to 0. Okay, so from that, we're going to factor out the e to the minus m vmp squared over 2RT. So we get e to the minus m vmp squared over 2RT times all this. Minus m vmp times vmp squared, we leave that separate for a reason, I'll show you why, over RT plus 2 vmp is equal to 0. So we said this can't be equal to 0. Therefore, all this must be equal to 0. So we can get rid of that and just say minus m vmp times vmp squared over RT plus 2 vmp is equal to 0. We're going to factor out the vmp, that's why we didn't combine them here. So we get vmp times minus m vmp squared over RT plus 2 equals 0. Now, so one obvious possibility is that your most probable speed is equal to 0, but that means your temperature is absolute 0, your system is at rest, and that's a trivial case. So we're going to ignore that possibility and say, okay, if the most probable speed is not equal to 0, it must be equal to, this must be equal to 0. So we come down here and say minus the molecular weight times the most probable speed squared divided by the gas constant divided by the absolute temperature plus 2 is equal to 0. We can move the 2 over here. Notice you'd have a negative 2, the double negative cancel out, so now we have positives here. And then we're going to just solve for vmp squared, and that's 2RT over m. So take the square root of that, and we have vmp, the most probable speed is just the square root of 2RT over m. Okay, so this is our curve, capital G of V. So V is speed, remember. So we got formulas for the most probable speed, the average speed, and the RMS speed. This is what they mean on the curve, remember. So we know VMP, that's at the peak here, where the derivative is equal to 0. Average speed is a little bit higher, and VRMS is even higher than that. All substances, all molecules, exact same pattern. So if we ratio this so that VMP is equal to 1, whatever, meter per second or kilometer per second, whatever, then the average speed is going to be equal to 1.128. And VRMS is going to be 1.225. So we've been doing all this. G is a calculation of speed, but instead we can look at it as a function of the translational energy instead. So we can write G of V like we've been doing, or G of energy of translation. Now we know that energy of translation is 1/2 times mass times the speed squared. So that solving for speed, we get speed is equal to the square root of 2 times the energy of translation divided by the mass of a molecule. Now we want to take the differential of this. Okay, so the differential of what we had on the previous page is the differential of speed is equal to 1/2 times 2 over m times 2 times energy of translation over m to the minus 1/2 power times the differential of energy of translation. Now I'm going to show a whole bunch of steps of rearranging this. It's just algebra. So like these 2's are going to cancel out. So we have the differential of speed is 1 over the mass of a molecule times 1 over 2 times the energy of translation divided by the mass of a molecule to the 1/2 power times the differential of the energy of translation Or we can rewrite that also as 1 over the mass of a molecule times mass to the square root of mass of a molecule over 2 times the energy of translation, the square root of all that, times the differential energy of translation. We could also say the differential of speed is equal to 1 over the square root of m times the square root of 2 times the square root of energy of translation times the differential of energy of translation. Or we could also say it's equal to the differential of energy of translation over 2 times m times energy of translation, the square root of the entire quantity together. Or we could, the final form we want is actually like this though. Differential of speed is 1 over 2m, the square root of that, times the energy of translation to the minus 1/2, times the differential of energy of translation. We are going to substitute all this into g of v dv. Notice we have dv, dv. And remember, that's the equal to the ratio that we started at the beginning of this section 4, I think, in. The differential of the number of molecules going at a certain speed divided by the total number of molecules. Now we're also going to use the formula we already found for speed. Speed squared is equal to 2 times the energy translation over m. So substituting these into the formula for g of v that I already showed you on the previous slide, we get the differential of the number of molecules with a certain energy of translation divided by the total number of molecules is equal to 2 pi times 1 over pi kt to the 3/2 times the square root of the energy, this should be translation obviously, times e to the minus energy of translation over Boltzmann constant times temperature times the differential of the energy of translation. Now, the reason we did this, remember, before we had g of e, it was a function of speed, but it also had the molecular mass, or weight of a molecule in it, which makes it material specific. Notice, in this form, we got rid of the lowercase m or capital M. There is no molecular weight in it. What this tells us then is that this is true for any substance, and it does not matter. We don't even need to know what the molecular weight of the substance is. So if you have some weird large goo of plastic, you have no idea what the molecular weight of your plastic is, you can still use this formula to find the same information. Alright, this is the last of section 5. We're just finishing up talking about the distribution of molecules based on energy instead of speed. So this is our sort of G function. So 1 over the number of molecules times the differential of the number of molecules with a certain energy of translation divided by the total number of energy of translation. So here we have different energy of translations for molecules. Our whole curve is a temperature of 300 kelvins. And the reason there's only one curve here is because it doesn't matter what substance. This curve, it would be true for helium, argon, neon, even methane. Methane, remember, it's also got vibrational and rotational energies. But what matters here is the translational energies. Okay, so continuing physical chemistry, chapter 15, we're doing section 7 now. We're going to be talking about molecular collisions and something called mean free path. Now we're going to make 3 assumptions for this section for now. The first, we're going to assume that molecules behave as hard spheres bouncing off each other. Obviously, molecules can be different shapes, but that's just going to make the math more complicated, and we won't benefit from that. And likewise, they actually behave more like sponges, but that's not particularly relevant either. So the second assumption is that the collisions are elastic. Remember, that means kinetic energy is conserved. So all the kinetic energy you had before the collision, there's still the same amount of kinetic energy after the collision. And then the third assumption is that there are no intermolecular forces except at the time of collision. In other words, we're talking about an ideal gas. So we're going to have 2 different molecules here. Molecule of type B, molecule of type C. So this is the size of one molecule. This is the size of the other molecule. So the distance from center to center here, I didn't draw that very well, but it's the radius of molecule B plus the radius of molecule C. Now we're going to be talking in this section about an imaginary cylinder. This imaginary cylinder is going to be the size of the entire both molecules side by side. Notice how they're just barely touching. So this is the time of collision. Again, this is because of our assumption that they're behaving like hard spheres. So the diameter of this cylinder is going to be equal to the diameter of the two molecules. So we're going to use lowercase d for diameter, and the diameter of this cylinder is going to be the diameter of B plus the diameter of C. And of course, I'm sure you all know that diameter is just twice the radius. So the diameter of this cylinder is equal to twice RB plus RC. Okay, before we can do any calculations for our collision rate, we need to define a few of these. Now, to make it more clear, the difference between an uppercase z and a lowercase z, I'm going to write a lowercase z is actually a cursive z here. So this lowercase z of B of C, this is the collision rate for one particular B molecule with any C molecule. Now this uppercase capital Z of B of C, this is the total collision rate for B molecules colliding with other C molecules. And this is all per unit volume. Likewise, an uppercase Z of B, this is total collision rate for B molecules colliding with each other. And this, again, is per unit volume. Now, back to lowercase z then, of B in parentheses B, this would be the collision rate for just one particular B molecule with any other B molecules. Now, the total number of B molecules then is going to be capital N subscript B, and the total number of C molecules then is going to be capital N subscript C. Now, we're going to try to calculate what is this one up here, this ZBC, capital Z. So the total B molecules with all other C molecules. So a collision occurs, remember, you got all these gas molecules flying around the room, and a collision occurs if the distance between them reaches that distance I showed you on the previous slide, the radius of B plus the radius of C, RB plus RC. Okay, also for notation, we have the average VBC. That's the average speed of B molecules relative to C. Now we want to find the volume of cylinder. I don't think I explained very well what the cylinder is. So we've got these molecules traveling around. Imagine if B and C were side by side for some reason, which they aren't because they're moving relative to each other. Then they're going to create a cylinder. Or no, imagine if, I got that backwards. If one molecule, it's spherical, it travels, it creates a cylinder. So if you imagine that whatever distance it's traveled times its diameter, that's the cylinder that it created. So anyway, so the height or length of the cylinder is just the average speed times the differential of time. So speed times time, you're going to get distance, basically. Now keep in mind that this cylinder can be much larger than the actual container because it'll bounce off the walls and just keep moving and moving. So it's not the cylinder is not a physical object. It's just the shape of the path that our molecule is traveling. So this volume of the cylinder then is going to be the area times the length. So the area is the diameter of B plus C times pi. So it's pi r. Yeah, it's pi r squared. The radius of the cylinder is both molecules together. Times the length is just the average speed times the differential of time. Now just V, this would be capital V, is the volume of the container. Not to be confused with lowercase v for speed, of course. So anyway, so the number of C molecules with their center in this cylinder, in other words, that we're going to have a collision with, is just the volume of this cylinder divided by the total volume of the container. And this could be greater than 1, remember, because, like I said, it just depends on what time frame you have. The molecule is going to keep moving because we assumed elastic collisions. And then that times the number of C molecules, because obviously if there's more C molecules, you're going to have more collisions. So the number of collisions which a specific B molecule makes with C molecules, in other words, whatever C molecules are inside this cylinder of travel, is going to be, like I said, lowercase zB of C. It's the volume of the cylinder divided by the total volume of the container times the number of C molecules divided by the change, your time frame. Alright, so now we've got an equation important enough, we're going to call it equation 1. So the speed, or the collision rate of a B molecule with C molecules is the number of C molecules divided by volume times pi times B plus RC squared times VBC, the average speed of B with relative to C. So this here is the volume of our cylinder times the ratio of the number of molecules. Now we want to substitute in for this average speed of B with relative to C here. Now remember, when a B and C molecule, they can collide at any angle. If they go in the same direction, we call it 0 degrees. And obviously here B would catch up to C if B is going faster than C. And likewise, they can collide opposite directions, 180 degrees, head-on collision, if there's such thing as a head-on for a sphere. Or they can be at 90 degrees, like B is going this way, C is this way. Or any other angle, doesn't matter. So we are going to use 90 degrees to represent the typical angle. So remember the Pythagorean theorem here. Whoops. If we have the velocity of B here and the velocity of C, then their diagonal distance, that's going to give you the speed, at least, of BC. So the average speed of B with relative to C squared is equal to the average speed or velocity of B squared plus the average speed or velocity, oops, that should be C squared, obviously. Okay, so remember from before we already showed the average B squared, or the average speed of a B molecule squared is equal to 8 times the gas constant R times the absolute temperature divided by pi times the molar mass of a B molecule. Or, yeah, the molar mass of B. And of course the same would be true then for C. The average speed of C molecule squared would be equal to 8 times R times T times pi times the molecular weight of C molecules. Okay, so that gives us, substituting back in, a formula for lowercase z of B of C. So remember, one B molecule against any C molecules is the number of C molecules divided by the volume of the container times pi times the radius of B molecule plus the radius of C molecule squared. That gives us the area of the cylinder, times 8 RT, R is the gas constant, T is absolute temperature, divided by pi, times 1 over the molecular weight of B plus the molecular weight, 1 over the molecular weight of C to the 1/2 power. So now we're going to prove that the number of molecules of B divided by the total volume is equal to the pressure of B times Avogadro's number divided by the gas constant R times temperature. What we're going to do is assume we have an ideal gas. So we're going to start with PV equals nRT. We know that lowercase n is just the number of molecules divided by Avogadro's number. So we get PV is equal to n over Na times RT. We're going to solve for V, and we get V is equal to n RT over pressure times the Avogadro's number. Flip that upside down, so we get 1 over volume is equal to pressure times Avogadro's number divided by the total number of molecules times the gas constant R times temperature. And then we're going to multiply both sides by the number of B molecules, which is really the same as N anyway, because that's what we're talking about, B molecules. So we have number of B molecules divided by the volume of the container is equal to the number of B molecules divided by the number of molecules in times pressure times Avogadro's number divided by the gas constant R times T. So that gives us back to where we started then, because we can cancel these two out because they're really the same thing. It's just the number of molecules. So the number of molecules of B divided by the volume of the container is equal to the pressure times Avogadro's number divided by the gas constant R times temperature. So if you have a pure gas, the radii, RB plus RC squared, is going to be the same thing, RB plus RB squared, and that's, remember, radius of B plus radius B is just the diameter of B squared, so it's the diameter of B squared. D subscript B is diameter of molecule B, just like DC would be lowercase, or diameter of molecule C. So the collision rate of one B molecule with other B molecules is equal to pi times the diameter of B squared times the square root of 2 times 8RT over pi times the mass of molecule B, or the molecular weight of molecule B, times the partial pressure of substance B, times Avogadro's number, divided by the gas constant R, divided by the total temperature. Now the total collision rate of B with C is going to be just the number of B molecules divided by the volume, times the collision rate of one B molecule with C. So that's going to give us the collision rate of B molecules with C molecules is equal to pi times the radius of B plus the radius of C squared times 8 times the gas constant times temperature divided by pi times 1 over the molecular weight of B plus 1 over the molecular weight of C, all this to the square root, or 1/2 hour, times the number of moles of B divided by the volume times the number of molecules of C divided by the volume. Now if we have a gas with itself, we need to multiply it by 1/2, otherwise we would actually be counting each collision twice. Collision molecule 1 with 2 and the collision 2 with 1. So the collision rate of all the B molecules with each other is going to be equal to the number of B molecules divided by volume times the collision rate of one B molecule with other B molecules times 1/2. That's going to give us 1 over the square root of 2 times pi times the diameter of a B molecule squared times the average speed of a B molecule times the number of B molecules divided by the volume of the container squared. Okay, so that gives us that the total collision rate of B molecules with other B molecules is 1 over the square root of 2 times pi times the diameter of a B molecule squared times the square root of this whole quantity here, 8 times the gas constant R times the absolute temperature divided by pi times the mass, the molecular weight of substance B. And then all that times the quantity squared. This quantity is the partial pressure of B molecules times Avogadro's number divided by the gas constant R times the temperature. Now, let's say we have the oxygen, diatomic oxygen. So the bond length there is 1.2 angstroms. An angstrom is 1 times 10 to the negative 8 centimeters. So the diameter of an O2 molecule then is roughly equal to 2 times 1.2 angstroms, or 2.4 angstroms. So assuming we're at 25 degrees Celsius, roughly room temperature, and just 1 atm, then the collision rate of oxygen molecules with other oxygen molecules is about 3.4 times 10 to the 28 collisions per cubic centimeter per second. And for reference, the average speed of oxygen molecules at room temperature then would be about 444 meters per second. Now we're going to talk about the mean free path, lambda. Lambda is the average distance a molecule travels between two successive collisions. So another way you could say that is it's the average distance a molecule will travel between collisions. Alright, this here is the last of section 7. So if we have a given B molecule, the distance that's traveled is going to be just the average speed of that B molecule times whatever time duration we're talking about. And t is going to have to be a long time, because obviously if you're talking about a really super short time, then you won't have any collisions. I mean, you got to be realistic to use an average here. So the number of collisions that B makes during that time is just going to be the collision rate of B with other B molecules plus the collision rate of B with other C molecules times whatever time frame we have. So that gives us that the distance, lambda, of B travels between collisions is going to be this distance divided by the rate. So the average speed of B molecules times the time divided by the collision rate of B with other B molecules plus the collision rate of B with other C molecules times the time duration. Notice the times cancel out. So the mean free path for a molecule B is just the average speed of B divided by the collision rate of B with other B molecules plus the collision rate of B with C molecules. Now if it's a pure gas, then of course the collision rate of B with C is going to be equal to 0. So that term will drop off, and then our mean free path is just going to be the average speed of B divided by the collision rate of B with other B molecules. Substituting in the formula that we had, then it'll give us the average speed of B divided by the square root of 2 times pi times the diameter of a B molecule times the average speed of B times the number of B molecules divided by V, the volume of the container. Notice that these two average speeds cancel out, and we showed before that NB over B is going to be equal to something else here. So this gives us the mean free path. It's equal to the gas constant R times temperature divided by the square root of 2 times pi times the diameter of B molecule squared times the pressure divided by Avogadro's number. Now, applications of this would be if you're the transport properties of gases. Notice that if you increase the temperature, you're going to increase the mean free path. But if you increase the pressure, it's going to decrease the mean free path. Now, for example, room temperature here, the oxygen molecules, their mean free path is about 1.6 times 10 to the negative 5 centimeters, or about 1,600 angstroms. That seems pretty short, but compare it with the size of an atom. It's actually quite a distance it's traveling relative to how big an atom is. Continuing on physical chemistry, chapter 15. Now we're in section 8, where we're going to derive the barometric formula. So this is not to scale, but this is Earth. It's a sphere, roughly speaking, and then it's surrounded by a thin layer of atmosphere. Again, this is not to scale or very pretty at all, but you get the idea. So we're going to look here at a very thin layer of atmosphere. Now, this thin layer of atmosphere, there's a lot we want to talk about. One, the height at the bottom of the layer is we're going to call Z. So the height at the top of this layer is going to be Z plus dZ. That's why I said this very thin layer, so we're going to use dZ, not delta Z. Likewise, of course, you know P is pressure, so the P pressure is going to be the bottom of the layer, so the pressure at the top of the layer is going to be P plus dP, the differential change in pressure. Now we have a force holding this layer up. This is PA. It's not phenol and aniline, it's pressure in the area. So force is pressure times area, so the area is going to be across whatever area you're looking at. We're going to be talking about a cylinder here, so A would be like the area of the bottom of the cylinder here, the area of the top of the cylinder here. Now the force down actually comes from two parts. One is just the gravity and the weight of this mass in here, but then we also have a pressure from yet another layer of atmosphere above. So we need to make sure we take that into account when we do our calculations. Now one thing that we said about here, this Z plus dZ, this dZ is going to be positive because we're increasing height, but we all know pressure decreases with height. So this dP is actually going to be a negative number. dP is less than 0. Let's see, so this is supposed to be an M, so the differential of the mass is whatever mass of this layer we have here, because it's made of gas molecules that's got weight. So the force up is just the pressure times the area I said, and the force coming down is the differential mass times gravity plus the pressure plus dP times the area. So that's the pressure from above. Okay, so continuing on about the layer of the atmosphere, we know that the atmosphere is in mechanical equilibrium because it's not rising or lowering or anything funny like that. So the force up is equal to minus the force down. Well, force up is equal to force down. They cancel out. Same magnitude, different direction, opposite direction. So remember the force up we said was the differential of mass times gravity plus the potential. No, this is the force down. Okay, I switched around on you. Okay, so the force down is the differential of mass times gravity plus the pressure plus the differential of pressure times the area. And that's equal to the force up, which is equal to pressure times the area. So we're going to distribute this A here, so we get the differential of mass times gravity plus the pressure times the area plus the area times the differential of pressure equals pressure times area. These two obviously cancel out. So we're going to solve for dP now and say, okay, the differential of pressure is equal to minus the differential of mass times gravity divided by the area. And that's going to be, well, just rewriting it a little bit, just minus G over A times dm. Now what we want to do is substitute out this dm. So we're going to use the ideal gas law. So we start with PV is equal to nRT. And remember that cylinder I showed you, the volume of that cylinder is the area at the bottom of the cylinder times the height, or the differential of height, dz. So we're going to put that in here, so we get pressure times the area times the differential of z is equal, and likewise for this number of moles, it's going to be the mass divided by the molar mass. So we have the pressure times the area times the differential of height is equal to the differential of mass divided by the molar mass of the atmosphere times the gas constant R times the absolute temperature. And remember, the molar mass of the atmosphere, it's got nitrogen, oxygen, and many others. So to use the right number, it needs to be a weighted average. It comes out to about 29.0 grams per mole. although realistically you might want to do that in kilograms per mole when you do it. Solving this for dm then, we have dm is equal to pressure times the molar mass of the atmosphere times the area divided by RT times the differential of height. Now we put that back into this formula up here for differential of pressure. So we get the differential of pressure excuse me, is equal to minus the gravity divided by the area times pressure times mass times area divided by RT times the differential of Z. This is the same area, so they're going to cancel out. So we just get equal to minus gravity times the pressure times the molar mass divided by the gas constant R times temperature times the differential of Z. Alright, continue on physical chemistry, chapter 15, section 8. So that gives us, we just moved the like terms over to the same side. So we have 1 over P dP is equal to minus mg over RT dZ. So remember, P is pressure, dP is the differential pressure, m is the weighted average molar mass of the atmosphere, g is gravity, r is the gas constant, T is temperature, and dZ is the thickness of this infinitesimally thick layer of atmosphere. Now we're going to set a reference point for potential energy at Earth's surface. So we're going to say the pressure at Earth's surface is P0, and then the height at Earth's surface is Z0. So always, potential energy is always arbitrary, but Earth's surface is a convenient reference point. So we're also going to say if the actual altitude we're interested in, Z, is Z prime, then the pressure up there is going to be P prime. The reason is because we want to write this as a definite integral. So we're going to add up all the atmosphere from Earth's surface to whatever height we're interested in. So we're going to take the definite integral from Earth's surface, P0, to our height of interest, that's P prime, of 1 over P dP, and that's equal to minus the integral from Earth's surface to height Z prime of mass times gravity over RT times dZ. Now we're going to make two assumptions when we do this integral. The first is that gravity is constant. Now, Earth's radius is about 6,300 kilometers, and almost all the atmosphere is below 42 kilometers. Now, 6,300 is a lot bigger than 42 kilometers. It's like 100 times as big or more. So what that means is that even though gravity isn't technically constant, out to 2 or 3 decimal places is close enough. Now, the other assumption we're going to make is that temperature is constant. Now, it's a long story, why not? But this is actually a horrible assumption. Temperature, it varies widely with altitude. It'll get hotter, colder, and like I said, that's a climatology thing we don't need to worry about. So, what that gives us is the natural log of P prime over P sub 0 is roughly equal to minus mg over RT times Z prime. And again, this is only approximate. That's why we use a wavy equal sign instead of a regular equal sign, because of this temperature approximation we made. Okay, continuing on physical chemistry, chapter 15. This is the last of section 8. So we're going to take that formula from the previous slide, take the inverse natural logarithm. So we get P prime over P sub 0, or P0, is roughly equal to e to the minus mg over RT Z prime. And then, of course, just multiply by P sub 0 to get both sides. This is still approximate, remember. So the pressure of interest at the whatever height is equal to the pressure at the surface times e to the minus mg over RT times whatever height we're interested in. This formula is called the barometric formula. And remember, it's approximate because we assume constant temperature, which is not really true. Continuing on in physical chemistry, we're in section 9 now. We're going to talk about the Boltzmann Distribution Law. Now first, let's start with an ideal gas. We know PV equals nRT, so solving for P, we get nRT times 1 over V. Now we want to get rid of this number of moles, so we're going to say P is equal to the number of molecules divided by Avogadro's number times RT times 1 over volume. Now we want to substitute this whole quantity back into the barometric formula. Remember, the barometric formula we showed in section 8 was pressure of interest is equal to P at reference 0 times e to the minus mgz over RT. So that becomes the number of molecules at height Z times RT divided by Avogadro's number times 1 over V, the volume, is equal to the number of molecules at height 0 divided by Avogadro's number times R times T times 1 over V times e to the minus mgz over RT. Now, like I said, the number nz means the number of molecules at altitude z that we're interested in. Now all these terms, the r's cancel out. Now since we're assuming constant temperature, remember the temperatures cancel out. So this really is an approximation again, just like we said with the, well, this formula was an approximation to begin with anyway. The Avogadro's numbers cancel out, and of course the volumes cancel out. So what we're left with is that the number of molecules at height z is equal to the number of molecules at height 0 times e to the delta E over kT. So now we've converted this into energy. So the change in energy, remember, is going to be the energy at height z minus the energy at height 0, or the energy from the pressure at height z minus the energy from the pressure at height 0. And that's just the mass of our molecule times gravity times our height. So we substituted that mgh and put it in here. And remember, this lowercase, this epsilon means the energy for one molecule. So now we have Boltzmann's constant here instead of R, the gas constant. So this is really an example of the Boltzmann distribution, but a special case of it. Okay, continuing on physical chemistry, chapter 15, section 9. So elaborating on what we did on the previous slide, the substitution. So we have this quantity mgz over RT in the exponent. We can substitute in this m is Na, well, this becomes the Avogadro's number times the mass times gravity times z, and then this R becomes K, NaT. Notice Avogadro's number is going to cancel out. So this whole quantity becomes mass times gravity times z over kT. And we showed about potential energy, it's mgh or mgz. So this just becomes the change in the energy. P is potential at the same pressure because it's due to pressure, but yeah, it's actually due to gravity. But this is the difference in potential energy divided by kT. And K is the Boltzmann constant, obviously. So this is what the actual Boltzmann constant. Let's say you have exactly two energy levels, like we were talking about Z0 and Z prime. And we have the number of molecules in energy level 1, the number of molecules in energy level 2. The difference in these two energies is just delta energy potential, delta epsilon P. So this is how the Boltzmann distribution law looks like. It's the number of molecules in state 2 divided by the number of molecules in state 1 is equal to E times the minus change in the energy, this would be potential energy or whatever, divided by kT. And this is a useful formula in statistical mechanics. Now, what this formula shows you then is that if the energy level in state 2 is greater than the energy level in state 1, then the number of moles or molecules in state 2 should be less than the number of molecules in state 1. And of course, delta G will be greater than 0. As a quick aside though, there are some scientists who, it's debatable whether or not negative temperature exists. And some scientists who claim to have created negative temperature in the laboratory, what they've done, they've actually managed to energize it so that energy 2 is greater than energy 1, but N1 is greater than or N2 is greater than 1. So they switch this around, and then doing the math, it works out to having a negative temperature. But it's still a positive amount of energy, so it's debatable whether it's really negative temperature or not. Okay, so let's say we have two different possible systems. Here, G, this vertical scale increasing. Okay, so in the first system, you have energy level 1, energy level 2, and they're kind of close together. So we have about half the molecules in energy state 1, half the molecules in energy state 2. But let's say we have another system with two different energy levels, they're farther apart. Then we're going to have is more the molecules in the lower energy state and less in the molecules at the higher energy state. So the larger the separation becomes, you should expect less and less molecules at the higher energy level. All right, continuing on the Boltzmann distribution, As an example, let's say at what temperature would the population of a state at higher energy be 1/10 that of the state at a lower energy, if the difference between those two energy states is 1 kilojoules per mole. So we're going to use the Boltzmann Distribution Formula. Number of molecules at state 2 divided by the number of molecules at state 1 is equal to E to the minus change in energy divided by kT. So we're just going to put in 0.1 for this ratio here, equal to E to the minus 10 to the third joules per mole times 1 mole over 6.02 times 10 to the 23rd moles. So we're doing that because we need to do this in molecules. So if this is the energy per mole, this will give us the energy per molecule. Then divided by the Boltzmann constant, 1.38 times 10 to the minus 23rd joules per Kelvin times temperature. And we just need to solve for temperature, and that works out to just 52.3 kelvins. As an example, though, another example, what about the electronic levels? We've been ignoring electronic levels in this class so far, and the reason is because the difference between the energy level, this delta energy, is huge. So here we go. N2 over N1 is equal to E to the minus 5 times 10 to the minus 19 joules divided by Boltzmann constant, 1.38 times 10 to the minus 23rd joules per Kelvin. And then even at 5,000 kelvins, it works out to this really small number. So this is the So basically what that's saying is that of all the molecules, if you have about 1,400 of them, just one will be in the higher energy state. All right, continuing on Physical Chemistry, Chapter 15, we're in Section 10 now. We're talking about the equipartition of energy. Now, in the time of the 1800s, there were 3 red flags that something was not quite right about classical mechanics. One of these red flags was heat capacity. So that's what we're going to be talking about now with this equipartition of energy. So the kinetic energy, remember, is 1/2 mv squared. But we have x, y, and z. So the total kinetic energy is 1/2 m in the x component of velocity squared plus 1/2 times mass times the y component of velocity squared plus 1/2 times mass times the z component of velocity squared. Now remember, rho is equal to mass times velocity. Alright, so the energy kinetic could also be written as 1/2 times the x component of momentum squared over mass plus 1/2 times the y component of momentum squared over mass plus 1/2 times the momentum squared over mass. Now here's the equipartition principle says, or the equipartition of energy. It says that the value of each of these quadratic contributions to the energy is the same. Equal, equal, equal. And it's equal to 1/2 kT for one molecule, or 1/2 RT for 1 mole. So, therefore, what we were doing up here, that we have 1/2 kT plus 1/2 kT plus 1/2 kT is equal to 3/2 kT, or 3/2 RT if you're talking about a whole mole. Now, let's talk about a monatomic gas such as helium. So the energy of translation is good for one atom, or one mole, one molecule, one atom, same thing. 3/2 kT for each atom, or the energy of translation is 3/2 RT for 1 mole, so the molar internal energy is just 3/2 RT. Alright, physical chemistry, this is the last of section 10 and the last of chapter 15. So then we know the molar heat capacity constant volume is the derivative of the internal energy, the molar internal energy with respect to temperature, holding volume constant. And that's equal to 3/2 R for helium, because all it has is the translational energy. X, Y, Z, that's 3 degrees of freedom. And each one of those degrees of freedom would be 1/2 R. Then, for a linear molecule, such as carbon dioxide, we have vibrational energy and rotational energy. So the vibrational energy is going to be equal to 3n minus 5 times RT, and remember, n is the number of atoms in one molecule. So, and if it was a non-linear molecule, then we'd have 3n minus 6 RT. Same thing, n is the number of atoms per molecule. But back to carbon dioxide then. So the molar internal energy is just the energy from translation, which is 3/2 RT, plus the energy of rotation, which would be 2 halves RT. Remember, you could have rotated 3 directions, so it should be 3 halves RT, except we have a linear molecule, so rotating about the axes, that does not count as a degree of freedom because it can't store energy that way. So this is just 2 halves RT. And then, of course, add the vibrational energy. From the formula up here, we get 4 RT. So the total amount of energy that the carbon dioxide will store is equal to 6 halves RT. Now, so the molar heat capacity, constant volume for carbon dioxide is 6.5 R. So if you take molar heat capacity, constant volume divided by R, that's just equal to 6.5. Now remember, the root of the equipartition of energy is classical mechanics, or Newtonian physics. So here's, well, like I was saying before about hints in the 1800s that something was amiss. So here's a graph of CVM versus R, of carbon dioxide versus temperature. Now, according to the equipartition theorem, at any temperature, the heat capacity should be exactly 6.5. So this horizontal line is the expected heat capacity of carbon dioxide. Now instead, you have some sort of curve. I just sort of eyeballed the exact value and shape. But the point is, it starts out low at low temperature, and with increasing temperature, it gets higher. There's only one temperature which the heat capacity really will be 6.5. And then it keeps increasing. And this is for another chapter to find out why that is.